Hello, fellow problem solvers! So today we're going to be doing a problem that is truly one of my all-time favorites, a historically beautiful problem from the 2010 IMO, problem number 5. This is an amazing combinatorics problem. It's a legitimate, medium, maybe even hard difficulty IMO problem. And this problem, if you aren't at a place where you can tackle a number 2 or number 5 at the IMO, that if you haven't ever done a number 2 or number 5 at the IMO, especially combinatorics problem, maybe you want to leave this one for the future, maybe. But if you have, I suggest you try this one out for a minimum of an hour, ideally 2 to 3, maybe even 3.5 hours, not more than 4.5 hours. And if you'd like to go along with us, give this a go for the next 15 minutes. And now let's begin. So, what do we have here? So we have these 6 boxes, and mind you, I love this problem. This is one of my favorite combinatorics problems of all time at the IMO, because there's zero theory here, right? There's nothing that's happening. There's 2 operations, mind you. We have these 6 boxes, and initially we're going to have 1, 1, 1, 1, 1, 1, and we can do one of 2 things. We can take one coin from one of these 5 boxes, take it out, and add 2 coins to this box, right? And then we'll have this situation, 1, 1, 0, 3, 1, 1. Or we can take, say, 1 coin out of one of these 4 boxes and exchange the contents of the other 2. So we have 1, 0, 3, 0, 1, 1. And now the question is, can we get from all 1s to a 0, 0, 0, 0, 0, and 2010 to the 2010 to the 2010. And this is a humongous number. 2010, 2010, 2010? Whoa, what is this? This has more zeros than actually more than I can count. If I'm being realistic, that's an expression, but this one has legitimately that many zeros. So, in these types of problems, ask yourself, for 5 minutes, pause. What is the first thing you do? And for me, the answer is, when I have no clue what's happening, the first thing I do is to play around with the problem, right? There's not much else that can be, there's no theory here, right? This is a completely new thing. There are these 2 operations. I'm trying to get to this. I'm really trying to see whether or not just applying these 2 operations, the contents of the last box can explode. And my question for you now is this. For next one, ask yourself for 2 minutes. How would you actually play around with this, right? How would you go around playing with the problem, okay? Pause now and ask yourself that before you begin playing. And now we're going to begin playing. I'm going to clear the board, and here's what I'm going to do. 6 boxes probably has a lot of complexity. Regardless of whether or not I can actually reach my goal, this is a huge amount of complexity. I can see that if this is even a question, then it's either I can reach this, in which case, wow, how am I creating from these 2 operations humongous numbers, right? That's the first question. Or secondly, the other question is, if this is not possible, and this is my 5th at the IMO, and there's probably also some difficult bounding involved. And also, how can we bound this doesn't seem to be just so obvious. So instead of 6 boxes with all coins 1, maybe let's see what we can do with 2 boxes or 3 boxes. And now's the time where you pause for the next 20 minutes and play with 2 or 3 boxes, see what you can get. Now let me clear the board and do some playing. Okay, so what can we do with when we just have 2 boxes, when we have 2 boxes with 1 and 1? Well, the only thing we can do really with box 1 is just double it, and then we get to 0, 3. Also, the notation is going to be box 1 through box n, left to right. Okay, and this is going to be the operation, some operations applied. And I can't really do operation 2 in box 1, so it doesn't make any sense. Now, in general, if I am, if I have an n here, right? I'm not going to deal with just 1s. I'm going to deal with some n's and a's and b's and c's, some other big numbers. If I say n and m, and only 2 boxes, say I only have box 5 and 6, what can I do? Well, the answer is I can only keep doubling this. There's nothing else I can do. And what will happen when I double it is I'll get 0 and then m plus 2 times n. When I keep doubling and doubling and doubling and doubling and doubling. Now, what happens when you go on to free boxes? Well, if we have 1, 1, 1, we can either get to, and I'm sure you found this if you played around, and I hope you did, you can either get to 0, 0, 7 or 0, 0, 6. Now, if you double this first and then exchange, and then double, you get 0, 0, 6. And if you double and then double, 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 you get 0, 0, 7. Okay. So now let's also look at generalities here. What is a general thing that you would look at? And I invite you to pause for the next 2 to 5 minutes and ask yourself, what is the thing that you would look at in this case? Okay? Now I hope that you've paused, because the answer for me is, I would go and say, okay, I want to say what happens when I have A, B, and C. And that might be a lot of things to think about. Okay, let me start off simply. So the simplest thing is if I have A and all zeros. And it only makes sense for me to look at if I have the A at the beginning and all zeros from there on. Okay? Now, the only operation I really can apply with this is a doubling operation like the switching around doesn't make a lot of sense. So let's say I actually have a double. Let's say I have doubled this. I have A, 2, and 0. Okay? And now what happens? Well, I have two options, right? I can double this, or I can do operation 1 on A, get this to 4, and I'll get an 8. So, and in either case, if I do first the doubling here, I'll get a 4, right? Let's see, A, and after that, so also does the sequence of operations matter? Well, yes, it does. It matters like when I'm switching around. So if I say double, I'll have A0, 4 here. And now what do? Well, I can get one from A and double it again, and then I'll be adding 4 to this side, right? Or I could switch it around and then double this. And what is the difference between these two operations? Pause for 2 minutes, ask yourself, what is the difference? And initially, it doesn't seem like there is much of a difference. Why? Well, you're going to get to A minus 1, 0, and 8 in both cases at the end. But think about what you did in the first operation. If you first exchanged them and then doubled it, what you've effectively done is you move from A0, M to A minus 1, M0 to A minus 1, 0, 2 times N. Versus in the other case, what you did is you moved from A0, M to A minus 1 to A minus 1, 2, M, and then you moved to M plus 4, 0, and A minus 1. And in the other case, you moved to 2M. Right, so in the latter case, when you first exchange and then double, right, this is what I'm calling, the second operation I'm calling exchange, the first one I'm calling double, sort of implicitly. Here I am doubling stuff. If I first exchange and then double, I'm effectively multiplying this, whereas here I'm adding it. Now, given we're going after this huge number, I'm going to need to assume like this doubling operation is more important, so to speak, right? So what do I do with that? So this means, what will I actually get if I have say I have A0, 0? Well, I'll get to A minus 1, 0, and 4 to begin with. Then I'll switch them around. I'll get to A minus 2, and then 0, 8 when I switch around and then keep doubling. Switch around again, A minus 3, 0, 16. I keep doubling, and what happens when I get to 0 here? Well, this is 2 to the power of this plus 1, so I'll get 0, 0, 2 to the n plus 1. Now, why is this very important? Pause for 1 minute to think about, why is it important? Well, it's important because I have found a way to get from an A, actually this is an A, to an exponent, right? I found a way to multiply through this operation, right? I'm just adding 2 coins, but I've effectively done sort of a multiplication type thing, okay? So that's what's cool, that's what's important about this operation. Now, what can we do when we have 4 coins? When we have 4 boxes, actually. 1, 2, 3, 4 boxes. And you may find, playing around, you can get to 0, 0, 0, and I believe 28. Like that's your maximum, no matter how you play around. But now take a step back and also ask yourself, what happens when I do other things? Also for this one, which we forgot, is to say, okay, what happens if I have A, B, and 0? Well, then the best thing for me to do is to switch this around, double B, and then keep applying this operation. Switch, double, switch, double, switch, double, switch, double. And by doing so, I can get to, I believe, from here to 0, 0, and 2 to the power of A plus 1 times B. So, or 2 to the power of A plus 2, or something like that. But what matters in this case is, effectively, I've multiplied sure by B, but I would have had a much better time if I had A plus B here, or A plus B over 4, for some bigger A and B, than if I had this situation right here. So that's also important to keep in mind, that this doubling and switching around operation is actually very, very powerful. I actually want to. Like, this is sort of potentially the best I can get from here. Now, what do we do with 4? I invite you here, pause for 10, 15 minutes, push the problem further. And now here's the next step. Let me clear up the board. So we found this operation playing with 3. Now let's see what happens when we have a 4, when we have 4 boxes. And 0, 0, 0, 0. And we'll move our way gradually up to 6. So what do we have here? Well, we could do the naive thing, apply this operation, and then just double it. But it seems like, is that really the best we can do? Right? Can we do better? And now let's see. So, can we maybe do some switching around and doubling to maybe apply this operation many times? I don't know, let's see. Well, the first thing we have to do is double, right? We have n minus 2, n minus 1, 2, a 0, and a 0. Now from here, I could get to, should I maybe double this? Well, if I do, I'll get from here, say doubling it, to getting to n minus 1, a 0. Or actually, wait a second, I want to, okay, if I double it once, I'll get 2 to the n. Actually, let me wait a minute, wait a second. So what will I get actually? If I subtract this once, and I get a 2, I can double this, I get a 0, get a 4, switch them around, I'll get n minus 1, 0, 4, and 0. Now I could double again, and that'll give me an 8. But now what happens if I was to switch around? Like, switching around seems to have given us this exponentiation thing here. What can it do with this? And so if I switch around, let's see this, I'll get n minus 2, 4, 0, and 0. Now this, I can say leave 1, and I can get from this like 4, 0, 0, I can get to say, so first I'll get to 3, 2, 0, then I'll get to 3, 0, 4, switch it around, I'll get to 2, 2, 4, 0, right? And then I'll get to, doubling it, I'll get to 2, 0, 8, and then n minus 2. And then I can switch it around, 8, 0. And now from here, I can get to 16, 0, 1. Switch it around, I get n minus 2, 0, 16, and 0. Now what did I do here? I multiplied this thing by 4, right? It's like, by having an extra padding, I didn't just multiply by 2, I multiplied by 4, applying the same operation. Or have I? Here's where I invite you to pause for 15 minutes and try to figure that out. And the answer is, well, let's look further. let's see what happens if we did again this switcheroo thing, right? Switch around, we get n minus 3, 16, 0, 0. So now what will happen is I'll always get n minus 3. So first the 16 will turn into 15. I'll get a 2 here, a 0 here. 15, 0, 4, 14, 4, 0. And then I'll double it again. I'll get 14, 0, 8. I'll get 13, 8, 0. And then double it, 13, 0, 16. I'll get a lot of stuff. I'll get 12, 16, 0. I'll get 12, 0, 32. Wait a second, so if I was multiplying by 4, I should have stopped by now, right? This whole process should have ended. If I was, actually no, I still need 2 more things to do. So if I, again, switch around, I'll get 11, 32, 0. And then I get 11, 0, 64. And now if I switch around, I get 10, 64, and 0. So if this was just multiplication by 4, this should have been a 0 by now, but it's a 10. I still have a lot of operations to go. So what is in fact happening here? I'm not just multiplying by 4. I am further exponentiating this thing. Right, so I'm getting from n minus 1. So what we had was first at n minus 1, 2, and then n minus 1, n minus 2, then a 4. And we get to n minus 2 and 16, or n minus 3 and 16. So we got a 1 and a 2 to the first, a 2, and a, what's it called? A 2 squared, a 3, and we got a 2 to the power of 4, right? This doesn't seem like, okay, maybe we're not exponentiating, maybe we're doing something different here. Now what is it that we're doing? So we're going to keep applying this and applying this. And the answer is when we get to n minus 4, how many times will we apply this? This exponentiation. Well, we'll get to 2 to the power of 16. So in essence, what we're having here is, and you can actually go ahead and try to prove this, and we'll actually need to prove this now, but what we're getting through this, so switching around process, isn't just multiplication. We're getting something along the lines of n0, to, where's this? N minus 3 and a 6. So we're going to get n minus n. So it's going to be a 0. And this is going to be 2 to the power of 2 to the power of 2 to the power of 2, 2, 2, and n minus 1 or n minus 2 2's. Now this is what we need, and 0's here. But this is sort of the thing we need, because this is closer to our humongous number. Like, this is a humongous number. If given n is huge, this is a humongous number. And now here, pause for 10 to 15 minutes, maybe 30 minutes. Push the problem further. See what it is you get. I'm going to clear the board, write up this actual second heuristic, try to actually try to see what it is we're getting. And here's the actual proof. And here's really the proof in words. So what we have is this. We have nk0, 0. And then we're going to get to n1, n1, 0, 2 to the power of k, by applying this almost, except for the n. And then from here, we're going to apply a switch, and another switch. Then we have n minus 1 and 2 to the k. So we move from n and k, 0, 0, to n minus 1. We subtracted 1 here, and we got 2 to the k over here. Now, this means we'll get a tower of 2's, so to speak, starting from n0, 0, we'll get, what will we get? So we start with n minus 1, 2, 0, 0. So this is a tower with 1, 2, and then we get n minus 1, 2 squared 0, n minus 2, 2 squared 0, 0, n minus 3, 2, 2, 2, 3, 2's, and then we'll at the end get actually n number of 2's here. 0, 2, 2, 2, so that we have n 2's, n 0, 0. Now, can this help us in our problem in any way, shape, or form? Remember, we have now 6 boxes is what we had, all at one point, and we've shown that we can get to immensely large sums, by applying these two operations. And I mean, especially this one is how we get to a very, very large sum. So is there somewhere here where we could apply it? Okay, now maybe there is. But the question remains, how are we going to actually end up using that? That also doesn't seem to be quite so trivial, so to speak. And here, now that this has been proven, I invite you to take a jab at this. Maybe even go for 5 if you don't feel comfortable right now. But how can you turn these ones into something humongous? Okay? Just try to get huge numbers. And ideally, you would like to try to get huge numbers over here. In this thing, what happens when you apply a variant of this operation on this? Pause for the next 20 minutes and try to figure that out. And here's the next step. So now that we've cleared this up, we have these two situations. And now let's see what we do here. Okay, so let's start maybe the simplest thing. We know that switching around and moving this number closer, a bigger number closer to here, gives us more options. Let's see if this with 4 is enough to give us a humongous number. So let's get rid of, say, instead of a 1, I'll write this as 0, 3, switch around once, switch around twice, I'll switch around, I'll move this here, 3, 0, 0, 0, 0, 0, and then I'll get, on these 4, I apply this operation, and I'll get 0, 0, 16, 0, 0, right, this is 2 to the power of 2 to the power of 2, and now I'll have a 0, 0, 0, and a 16, 0. Now, what is this number in comparison to 2010, to the 2010, to the 2010? Right? What is this number in comparison to it? Like, I can even get now bigger numbers, but what is the relationship between this tower of 2's and 2010 to the 2010 to the 2010? Pause for 5-10 minutes. Think about it. I have 2 to the power of 2. This is actually becoming pretty funny to me, like what this is turning out to be. How do you compare this tower of 2 and 2010 to the 2010 to the 2010? Pause for 5 minutes and think about it. And here's how you do it. And the answer is there is no comparison really, because say 2010, like now if you do some computer science or just memorize the powers of 2 till some point, you know that 2048 is 2 to the 11th. Okay, so this 2010 to 2010 to 2010, well, this thing is definitely less than 2 to the 11th, to the power of 2010 to the power of 2010. Okay, now what is this? Well, this thing right here is 2 to the 11th times 2010 to the 2010. Okay? Maybe if I estimate this, what happens there? I can estimate 2010 to be, I'm going to estimate this actually to be less than 2 to the 11th again. 2 to the 11th times 2 to the 11th to the power of 2010. Now this is equal to 2 to the 11th times 2 to the 11 times 2010. Now can I estimate this with my tower of 2's? That's what I mean, like this is not even close. Like this number right here is going to be less than, I have names for these numbers. I totally forgot about this. This number over here is 2 to the power of something. Now this something is less than a 4, right? is less than 2 to the power of 16. Yeah, this is actually, is it less than 2 to the power of 16? So this is less than 2 to the 11th. And yeah, I think it makes sense, 2 to the power of 16th. So this is less than A4. Let me actually double check this in my own time. And actually there's so many ways that we can actually go about doing this. One way is to say this is 11 times 2, say this is 2 to the, say, 11 times 2011. Still doesn't change our estimate that much. And now this thing right here is less than 2 to the power of A5. And this is less than A6, which is less than A16. Much less than A16. So we have a number here that is many orders of magnitude bigger than our A. Now, what do we do with that? Pause for 5 minutes, maybe 20 minutes and try to solve the problem? And the answer is, well, we can apply operation 2 on, even if there's nothing here. So we can keep decreasing this. And mind you, we're trying to get, let's call this number A, 2010 to 2010 to 2010. I can decrease, this is an even number. A over 4 is a number I can reach. I'm just subtracting 1 from this at every single point. And I can continue doing that until I reach from this to 0, 0, 0, A over 4, 0, and 0, just by switching around and getting nowhere. And then I double once, I get 0, 0, 0, A over 2, 0, and I double again, and I get to what I need to do. And this finishes up the problem. Now, it's a difficult combinatorics problem, and I like it because, mind you, this is the only theory you needed, by the way, estimating this. And I sort of half-assed it, mind you, I didn't really do it fully. But I think it's decent. You can let me know in the comments if it's not. But the main thing with this problem is that it's just creativity. Like, there's nothing here, there's theoretical that you can really point to. It's just doing the next thing, playing around and figuring out how to get humongous numbers. Now, there's a story that a deputy team leader complained to the team leaders that the problem was too hard because it didn't contain whether or not this was possible. It's like, try to find out if you can reach this number. Not show that you can reach the number, but find out if you can reach it. And the complaint was that some deputy leaders couldn't complain to the actual leader of some IMO team that this problem was too hard. Some of us, deputy leaders, thought that we actually couldn't reach the number. To which the team leader responded with, well, that is why you're the deputy leader and not the team leader. So that's a little bit of a story with this problem. This finishes it up. It's absolutely beautiful to me. One of my top favorites of all time. And as always, thanks for problem solving.